I would like to start with a conclusion that we recently made in our group, and this is that quantum annealing on its own is very often not able to solve combinatorial optimization problems that are actually hard classically. I'm not talking about these 20, 30, 40 qubit problems like max cut, exact cover, spin glass problems. Yes, we know that they belong to a hard complexity class, but and then we can find a nice quantum speed up over classical random guessing. However, these problems are actually classically easy to solve. So it's really a matter of seconds to solve them on a classical computer. And I want to talk about large-scale problem instances, so really thousands of qubits where classical solvers also start to struggle. So really where they take hours or maybe a day to find a low energy state. And in Jülich, we spent now many years working with industry partners to really take large-scale real-world problems, putting them on our quantum computer, for example, our DWave machine here, and nowadays also the Pascal Fresnel system. And what we generally observe is that while we can get very low energy states very easily, the quantum annealer is almost never able to really find the global minimum, so really the solution to the optimization problem. And we spent a lot of time really investigating this. So why is quantum annealing failing? What's causing these bottlenecks in the algorithm, and how do they relate to the optimization problem? And with all these insights, we then designed our learning-driven annealing algorithm. Learning-driven annealing is a framework for quantum annealing, so it uses quantum annealing as a sampler. And the idea is here really to realize practical quantum optimization with the machines that exist today. So we are not adding any new terms to the transverse field Ising Hamiltonian, because on the real devices we cannot do this. We are not changing the annealing schedule in any way, because this is also very often physically limited on the devices. And instead, we found a nice way to adaptively modify the problem Hamiltonian. And by doing this, we can guide the system through critical regions in the time evolution. And in doing so, we can actually solve very large optimization problems now with these machines. And I will later show you some benchmarking results where we can see that we now obtain run times as well as solution qualities that are very competitive to classical solvers running on our supercomputer. So I will start with a quick overview of why quantum annealing is failing. Then I will continue and showing you how we can overcome these limitations. And then I prepared two example applications, which is a large-scale spin class problem, 5,500 qubits, and a prime number factorization problem with over 1,200 qubits. So to get everyone on the same page, I have here an overview of how we do quantum annealing. So we start here on the left-hand side with our optimization problems. I will consider today aircraft scheduling, spin glass, and prime factorization problems. We encode them into an Ising Hamiltonian here with two-body interactions. Of course, we could use larger interaction numbers, would maybe improve, but this is really what we can do on the devices, so we stick to that. We then embed the optimization problem on our real hardware. We have several devices here that we could use, but I will focus on the DWave Advantage systems 1 and 2. And then we run the annealing algorithm. I'm using here the standard sum of Pauli X drivers again, because this is what is implemented on the devices. And as the annealing schedule, I'm using here whatever is native to the machine, so in this case, the quadratic schedule for the DWave. So as you can see, we're using here a very vanilla version of quantum annealing, nothing special yet. And when we apply this to some optimization problems, we get results like these. So let me start here with the spin glass instance. So spin glasses occur, for example, in material science. We are considering here a NUT7 instance, which means that all the biases are 0, and the couplers, they're from a set that is plus minus 1 over 7, plus minus 2 over 7, all the way to plus minus 7 over 7. This particular instance we are looking at here, this is not taken from a real-world example. It's more meant as a benchmarking tool for the DWave machine. So in this case, the problem is really native to the hardware. So we're using all the 5,580 qubits of the Advantage 1 chip and the 45,000 couplers, roughly. This problem, since we have both antiferromagnetic and ferromagnetic couplings of roughly the same size here, it's classically very hard. I will later show you some benchmarking results, but it's really not easy to solve it. We have here an energy landscape with a number of local minima that scale in the order of 2 to the power of 50, 2 to the power of 60. And the energy gap between the local minimum and the global minimum is also very, very, very small. When we run this on the quantum annealer, we get results that look something like this. So here on the x-axis, we have the Hamming distance to the best known state, y-axis the energy distance, and each blue dot here, this is a single sample that we get from the quantum annealer using this vanilla quantum annealing. As you can see from the energy, I would say like on average we have an energy distance of like 70. The best state here has a distance of roughly 20. When you consider the total energy range of the problem is 10,000, so very close to the global minimum in this case, really in the sub% range. However, even when we take here the best state, we still have a Hamming distance of 1,000 from the actual global minimum. So as you can see, we can get very low energy states, but even the best states that we get are still very, very far away from the solution to the optimization problem. Well, this might not be a huge problem with the spin glasses, since this is mostly an optimization problem. When we, for example, look at factoring problems, this is indeed a big problem. So what you can see here is a multiplication circuit that we can use to do prime number factorization, in this case 1,240 qubits. And we get this droplet-shaped distribution here. Again, regarding energy, we are quite close to the global minimum, but regarding the Hamming distance, we have on average a distance of like 500, 600, so half of the actual problem size. And since these factorization problems, they don't really have an optimization part in them. They're just a list of constraints that need to be satisfied. So in this case, only the global minimum over here is actually solving all these constraints and being really a solution to the optimization problem. So having all these low energy states basically means nothing. We cannot really use them. So in this case, also, the quantum annealer fails to solve this. And as a last example, I have here an aircraft scheduling problem that we did together with Boeing. This is a very small instance from the set that we solved. We solved larger ones, but this is just to stretch my point here. So this is a 24-qubit optimization problem that we did on the Advantage 2 chip in this case. So the embedding is also here relatively native, so at maximum a 2-qubit chain. And so this scheduling problems consist of an exact cover problem. So this is an optimization really part, and then we have several constraints that need to be satisfied. You can actually see these constraints in the energy landscape down here. So you see these 3 wells. This is really where the constraints are satisfied, and then the energy of these minima is determined by the exact cover optimization part. In this case, the solution is in this well down here, but you can see by these red dots here, these are the samples that the quantum computer prepared. So you can see, like all these samples are in this local minimum well, and we never sample a state that belongs to this well or to the solution well. So we have here 3 applications related to real-world problems of different sizes, from small to very big, where the quantum annealer really fails in solving them and finding the ground state. So how can we overcome these limitations? The answer is iterative quantum annealing. The idea here is that we take the samples that we get from the quantum annealer, and then we iteratively change something about the annealing process. When you look at this equation up here, so this is the time-dependent Hamiltonian that we're using. We have basically 3 turning knobs that we can adjust. One of them is the annealing schedule, so this beta and this gamma function here. This is what I call here schedule engineering. So the idea is that adiabatic theorem says if we do the annealing slow enough compared to the instantaneous energy gap, we remain adiabatic. So when we have an avoided level crossing, so a small gap, we can slow down in the vicinity of this gap and accelerate on outside of this. To remain in the same annealing time frame, but to be more adiabatic. The problem with this is, so there are actually two problems. The first problem is that we need to know where this gap is, and especially here for the scattering problems and these factorization problems, we have perturbative crossings. So in this case, we would need to know where this gap is exponentially precise. So this is an issue. The second issue is that on the hardware, these schedules, also they depend on the hardware, so how fast we can change the pulses and so on. So for example, on the DWave chip, we have 10 time points and a maximum slope that we can set, so we don't have that much control really in changing these annealing schedules. So really, adjusting here or optimizing beta and gamma is something that we can do. It gives us a slight improvement, but really it does not help us to really solve these problems. Going in a similar direction is reverse annealing. Here the idea is we start from a good classical state, anneal backward, wait for some time, hope that some quantum effects happen that bring us to a low energy state, anneal forward again. This method has been popular a few years ago, but recently there are many articles, papers coming out that say reverse annealing really just works through thermal relaxation. So what's really happening is you start from high energy state, you anneal backward, your system thermally relaxes while you wait, and then you get a better state. But this process also works in reverse. So if you already are in a good state, you anneal backwards, this can actually excite you and you end up in a higher energy state. So in practice, reverse annealing can be used to some degree to do something like local search, but it's really not able to cross large energy barriers, and it's especially not able to solve these optimization problems. So changing the schedule here is not an option. What else can we do? We can target here the driver Hamiltonian, and we have heard a lot about this. For example, in the talks from Natasha and Rupayan and Paul about adding like XX terms to this. We could also think about adding Y terms or other drivers. Well, this in principle works very well in simulations. The issue is, of course, we don't have a device where we can really implement this yet. So maybe the gadget that Paul was presenting might be a way out, but still there's significant limitations to this. It's not just a plug-and-play approach that we can do right now. So changing the driver is also not an option. So the last thing that we can do is actually modify the problem Hamiltonian. This is exactly what we want to do. We call this here learner-driven annealing. So the idea is we take the samples that we get from the quantum annealer, we analyze them, and then we modify them. So we modify the biases and the couplers, and then we use this modified optimization problem and do the annealing again. And then we take the samples that we get from this modified optimization problem, we evaluate them again with the original problem Hamiltonian, so that we're not cheating here in any way in energy, and then just we continue this iterative process. And by modifying this optimization problem, we can remove avoided level crossings selectively, really, from the instantaneous spectrum, and thereby help the time evolution to really stay in the instantaneous ground state. We have designed several protocols here, local global search, tunneling protocols that are really meant for different kinds of bottlenecks that can occur during the annealing. And in these animations here, you can see how this looks in practice. So example here for the spin glasses, we start with this blob of states here. And as we then apply these different iterations, you can see that we converge here to the actual solution of the optimization problem. And you can see here that what's really remarkable here is that we can cross here significant Hamming distances. So really here, Hamming distance of 1,000, something that was before really not possible. Same thing here for the factoring problems, where we also converge the solution, and as well as here for the scheduling problems. So you can see these three real-world optimization problems that we were not able to solve before, we can now solve with learner-driven annealing just by changing a bit the problem Hamiltonian. So how does this work? To understand how this works, we have to look at the instantaneous energy spectrum and its relation to the problem Hamiltonian. I've prepared here a 20-qubit spin glass-ish problem instance that we'll consider throughout the rest of this talk. So what you can see here is an instantaneous energy spectrum for this 20-qubit spin glass problem. X-axis is just the annealing parameter. So here at s equal to 0, we are just in the driver Hamiltonian, and here the problem Hamiltonian is at s equal to 1. Y-axis is the instantaneous energy normalized to the gap size of the driver. So you can see at the beginning we have this gap of 1 between these two states. You can see that some of these states are colored in blue, red, and green. This is because these states end up in a minimum of the optimization problem. So the blue curve here, this denotes a global minimum, and the red and the green curve, these are local minima. And the rest of the states are states that belong to the wells of these minima, so they have Hamming distance 1, 2, and 3, and so on from these states. You can see that we want to end up in this blue curve at the end, and you can see that we have some avoided level crossings here, and a very narrow one over there. The idea of learner-driven annealing is now that we can relate these avoided level crossings to certain characteristics in the problem Hamiltonian. And to see this, we have to look at the energy landscape. So here's the energy landscape for this 20-qubit problem. XY axis, think about it as Hamming weight, for example. So having a state here and here, they have a certain number of spins that need to be flipped. The z-axis here is the energy, and you can see it's a quite complicated optimization landscape. We have several energy wells and minima in here. The global minimum, so the blue state is located over here. The red one is located over here, so it's a very wide well here, and the green state is located over there. When we now look, for example, at this transition over here, this is what we call a many-body localization transition. The idea is before this transition, the system is in a paramagnetic phase. You can see this here by the fact that we have overlap in all of these wells at the beginning. But as we transition through this avoided level crossing, you can see that the system localizes in one of these wells. The interesting thing here is that the system actually localizes here in the local minimum well and not in the global minimum well over here. And this is because this well is much wider at the bottom. So here where the driver is still very active, it's just energetically more favorable to get into or localize into a well where this state vector can be spread out more. As a result, since we are now localized in this one, eventually the system has to tunnel from this well into the global minimum well, and this is exactly what we see here at this narrow crossing. This is what it's a quantum tunneling event happening here. So really the system tunnels from this well through this barrier over here into this well. And when we look here at the phenomenon entanglement entropy, you can see that the first many-body localization comes with a continuous peak here, and the tunneling transition here is really with a discontinuous jump. So this indicates the first order phase transition, and the first one here is the second order phase transition. The important observation that we can make from this is that these transitions, these avoided level crossings, are always related to the presence of wells and how they interact. So if one is wider, one is maybe steeper or whatever. And we can exploit this, and this is exactly what we do in learning-driven annealing. So we modify the problem Hamiltonian. By doing this, we modify the energy landscape, and by doing this, we can modify which transitions actually happen here. By doing this, we can help the system, guide the system into the global minimum. So how do we modify the energy landscape? We do this by using what we call features. So if you take a classical state, just a normal computational state, we call it here alpha, we can identify all those couplers and biases that are satisfied by this state alpha. Satisfied means that they give a negative energy contribution. You can see here on the left-hand side, these are all the couplers and biases present in this 20-qubit spin glass. And when we, for example, look at this local minimum over here, you can see that we satisfy this set of couplers and biases. If you look at the different state, for example, this global minimum here, you can see that we have a different set of couplers and biases. And as I go back and forth, you can see these sets are completely different. While on the other hand, if I look at a state that belongs to the same well, for example, this one here, you can see that we have this set. And as I go back and forth, you can see that they are relatively similar. And there are two observations that we can make here. First one is that these sets of satisfied terms, they actually act as a kind of fingerprint. They really identify a well and this region of the Hilbert space. And the second observation is that these are all the terms that give a negative energy contribution to this state. So they are really responsible for having an energy well at this position. And this brings us to the idea of the feature Hamiltonian. So feature Hamiltonian is basically the problem Hamiltonian, but we remove all the terms, all the biases and couplers that are not satisfied. So by doing this, we effectively remove all the other wells, because we remove all the other terms that can create a well outside our reference state. And this animation here, you can see how this looks in practice. So what I show you here is an interpolation going from the problem Hamiltonian to the feature Hamiltonian. You can see that we effectively remove these two wells here when we select this global minimum here as our reference state. You can actually prove that at the end, this energy landscape, this deformed energy landscape, is completely monotonic in Hamming distance from our reference state. So all points are basically pointing towards our reference state. And since we know that the relationship between wells is actually causing avoided level crossings, we can now assume that the instantaneous energy spectrum becomes much more simple. And this is exactly what happens here. So this is the instantaneous energy spectrum using the feature Hamiltonian. You can see here this blue line. This is exactly our global minimum state that we set as a reference state. And this blue and this green line, so the local minima here and here, you can see that these states are effectively shifted up. And they very quickly leave this shaded area. This is the gap size of the driver. So this means that once they left basically this shaded area, solving this with quantum annealing and staying really in this blue state here is completely trivial. The interesting aspect is now when we look at what this really means in terms of the problem Hamiltonian, so of the original problem Hamiltonian. So you can see down here, this is the instantaneous energy spectrum using the original problem Hamiltonian. So you see it does not change as we change here our energy landscape. The only thing that changes is this yellow curve here. This yellow curve denotes an annealing simulation that we did with the feature Hamiltonian and then just evaluated the quantum state vector in the original spectrum here, so with the problem Hamiltonian. And you can see that initially we are following this red curve here, so this means that we localize in this well over here and we are not able to do the tunneling into the global minimum. But as we change to the feature Hamiltonian, you can see that this yellow curve is leaving this red curve. It's actually doing the transition here at the many-body localization transition point into this blue curve over here. So effectively, using this feature Hamiltonian, we modified this many-body localization transition and told the system what it should do, if it should stay in this red state or go into the blue state. Of course, we are not limited to just force it into the blue state. We can also use a different feature Hamiltonian to force it into the green state. So here you can see that we manipulated this many-body localization into the blue state and then this many-body localization into the green state. So in the end, we end up in this green local minimum. So you can really view this feature Hamiltonian as a tool that gives us access to the instantaneous spectrum, and we can manipulate how the system traverses through this. So far, of course, we have used the fact that we know this state in order to end up in this state, so we haven't gained much yet. And this is where our protocols that I showed you in the beginning, so it's local search, global search, and so on, come in. So the idea is that we can take the samples from the quantum annealer, and we have the protocols to manipulate all the different kinds of avoided level crossings that can happen. So many-body localization, all these perturbative tunneling transitions, as well as some local transitions within the wells. Unfortunately, I don't have time to cover all these algorithms, but I have time to cover one of them, and it's, I brought you here this global search that we did with learner-driven annealing. You can see here a different energy landscape that has 4 local minima, so 3 local minima and 1 ground state, and here's the instantaneous energy spectrum for it. The idea of learner-driven annealing is that we, of global searches, that we can manipulate a single many-body localization transition just from the samples that we get from the quantum annealer. So the idea here is that we, through other algorithms, before we found this local minimum over here, so this yellow state here, this belongs to this red curve. The blue curve, the ground state, is located over here. The green curve is located here, and the purple curve is located over here. So this is the local minimum. The idea is now that if we would use the feature Hamiltonian with this known local minimum, what would happen is that we force the system to follow this blue curve, and then this many-body localization leave the blue curve into the red curve. So we don't really gain anything. So what we want to do in this global search is we want to manipulate this many-body localization. In order to do this, we have to get rid of these other localization transitions that happened before, so this purple and this green one. And we can do this because we already know the path that brings us from here to this many-body localization transition from the feature Hamiltonian that belongs to this state over here. The only thing is that we need only a part of this feature Hamiltonian, so basically only this part that brings us from here to here, and not the part that brings us from here to here. So the way we're doing this is we just use a normal problem Hamiltonian, just normal annealing. We sample all these states that belong to all the energy wells over here. What we then do is we look at all the features of all these states and we compare it to the features of this yellow state, so our reference local minimum. And we then only apply the feature Hamiltonian to those features where all of them overlap, so where they all agree. So in this case, if you do this, you can see that we effectively remove this first local minimum over here. So this purple curve is now shifted up, and we prevented a transition from blue into the purple curve. So in this case, effectively, we identified here that this first alpha domain is set in a certain configuration. And when we continue this, so doing this same thing again, we can remove the green transition here. So this local minimum is now removed, and we end up with the situation where we have isolated this many-body localization transition. In the energy landscape, this looks something like this. So we end up with a double well potential where we have our initial local minimum and the other well, which has a lower energy. In this case, it's the global minimum. So what we can do now is we can just sample from this. Since this is a many-body localization transition, we will sample states from both wells. And we can then just say, OK, all the samples that have a certain Hamming distance from our initial state, we count them as a state from this other well. Then we can apply our local search protocol, which then removes this well. And so we end up with just the blue curve over here. So just by doing these four iterations, you can see here that we effectively force the system to stay here in the blue state and prevent this many-body localization into the red state. This is just one example. We have local search that can do transition within a state. We have this global search for this many-body localization. We have a tunnel protocol for this perturbative crossings, and many more for specific applications. Yeah, so now that we know how this roughly works as an algorithm, I have here some applications. And the first one I want to talk about is prime number factorization. I'm sure when all the people here think about prime number factorization, most of them will think about Schulz algorithm. Of course, has a proven speed up, but we know that we need thousands of qubits to really realize this on a gate-based quantum computer. So the idea is that we can already do prime number factorization on the quantum annealer in terms of an optimization problem. So the idea is we start here with an integer n that we want to factorize into the prime numbers a and b. So we can formulate this optimization problem here where we want to find a and b to minimize this expression. We can solve this using quantum annealing by formulating multiplication tables. So basically what we do is we take a, b, and n, look at them in their binary representation, so with all these bits here, and then we can form this multiplication table. The reason why we're doing this is because there's a paper from Ding et al. That show that we can implement this multiplication table natively on the DWave hardware. So what we can do is, you can see that we always have this multiplication of one bit A0 times B0, for example, and this can be implemented in terms of a controlled full adder gate. And these controlled full adder gates have a native embedding to these 8-qubit unit cells that we find on the Advantage 1 system. So you can see here, this is basically doing the multiplication, and then we have the outputs here to the next unit cell. So you can then just take this structure and repeat it. And yeah, then you end up with something like this. So you can see each blue cross here. So this is the DWave chip. All the blue dots are qubits that we actually use, and each blue cross is one of these unit cells. So it's implementing one of these controlled full adder gates. In their paper, they were able to get up to 23-bit factorization using reverse annealing. So naturally, we tried the same, but using learning-driven annealing. So what we're doing here is we take the same 23-bit number, so 8,200,000, whatever, and yeah, we want to factorize this. Here on the right-hand side, you can see the Hamming distance from the solution, and this is the y-axis is the ng distance. The colors here denote the different iterations of the algorithm. So initially, these are the blue dots, quite hard to see, but I think you remember this droplet-shaped distribution that I showed you in the beginning. So again, we sample basically states that are here in the middle of around 400, 500 Hamming distance from the solution. And with each iteration, you can see that we here converge to the solution. And here on the left-hand side, you can see the average magnetization of each bit. And here, after roughly 6 iterations, the whole system converged, and we found the solution. Actually, I think we found the solution already after like 3 iterations, but in this case, really the algorithm converged. So they were able to just go to 23 bits. Above that was just not solvable using reverse annealing, but we still tried. So here you can see a 25-bit number, which is like, let me lie, 33 million or whatever. And you can also see that within these 7 iterations, we are able to converge to the solution. So we didn't stop at 25-bit. We went all the way to 28-bit. This is like now 266 million as a number that we factorized. And again, within the 7 iterations, we are able to converge to the solution. And we had to stop here at 28 bits just because yeah, we weren't able to fit a larger multiplication circuit on the DWave hardware. You can see that we exhausted here really the height of the chip. But to my knowledge, 28-bit is actually the record on the DWave, and also with a quantum computer, as long as you don't use very heavy classical post-processing. So this is really running this optimization on the DWave, getting the result right away. Okay, so much about prime factorization. The other problem I want to talk about is spin glasses. Again, we are using here this NUT7 spin glass with 5,580 qubits. What we did here is a comparison about comparing our approach on the quantum annealer to other quantum strategies on the DWave, as well as to classical solvers on our supercomputer. So for the quantum strategies, we used here our DWave Advantage 5.4 system at Jülich, and for the classical solvers like simulate annealing and here Gurobi, VeloxQ, Toshiba simulated by bifurcation machine, we used one node of our supercomputer using 4 NVIDIA H100 GPUs and 4 Intel Xeon 8168 CPUs. Here on the x-axis, you can see the wall clock runtime. So it's really the total time of execution from hitting start button and getting the solution. The only thing that's excluded here is really waiting times in queues. So when we submit something to the quantum computer and we had to wait, we excluded that. The same goes here for the supercom computer. If there are some waiting times, we are not including them here. Let me start here with learn-driven annealing. On the DWave, we used here 2 of our protocols, local search, global search, in a very simple alternating fashion. In total, I think we did here around 50 runs on the DWave, 50 times sampling the DWave. And you can see after roughly 6 minutes, we found here the best known state for this one optimization problem. When we compare this to other quantum solvers, so we have here forward annealing, it's just scattering around this initial value that we also used here for our algorithm. With reverse annealing, we were able to get slightly lower energies, but as I said, it's limited to thermal relaxation. So in this case, just do local search and get stuck in a local minimum. We also tried here cyclic annealing. And this is a combination of using reverse annealing and the H-gain feature on the DWave. But again, this was only doing some kind of local search, was not able to cross really large barriers. So already with the first iteration of our local search, we obtained here energies that are as good as they could ever do, basically. We then tried classical solvers. We used here an in-house developed simulate annealing for our HPC system, and as I said, these proprietary solvers. Interestingly, the simulate annealing worked the best on these spin glass problems, and it was the only algorithm that was able to match the lowest energies that we found with learn-driven annealing, at least for 2 of the instances, of the 10 instances that we investigated here. But still, you can see here that the runtime is in the order of 20 hours, roughly. So yeah, we're much faster here. The question is now, is this quantum advantage? Clearly not. The thing is that, of course, the runtime here for the classical solver scales with the resources we give them. So in this case, we use 1 node of the supercomputer. We could easily have used 10 nodes, 20 nodes, and so on. And then, of course, the runtime would scale down here. What I want to highlight here is instead that with learn-driven annealing, we're now enabling the quantum computer to, first of all, solve these problems, something that was before not possible. As you can see here with the other methods, we are not able to solve them, but now we are able. And additionally, we can make use of these very fast sampling capabilities that we have on these quantum annealers to get runtimes that are very competitive to other, also classical solvers. And this brings me to my conclusion. So I've showed you that quantum annealing has its limitations, and mainly due to avoided level crossings and these many-body and perturbative crossings. And I showed you that using this feature Hamiltonian, we're able to manipulate these instantaneous spectra and effectively guide the system through these critical regions. I've shown you how we can use this in a sort of hybrid quantum classical procedure to mitigate hardware limitations like short annealing, short coherence and short annealing times. And I showed you that this works on the DWave Advantage system with over 5,000 qubits. And I think the takeaway is really that we can now use this learn-driven annealing to solve problems on the quantum annealer with very competitive runtimes and lowest energies to classical solvers. With this, I'd like to thank you. Happy to take questions. Yeah.
Yeah, thank you very much for this very nice talk. There's actually plenty of time for questions, so don't be shy. Yes.
Yeah, great talk. So you mentioned that you were using like vanilla sampling, like not changing much configurations, but I could see how maybe there's some configurations that could benefit. So maybe, do you have an intuition for that? Like maybe you could use more exploration, so maybe you could use a faster anneal, or...
So you mean really changing the annealing time or the schedule, or?
Yeah, but then just keeping one, not exploring it. Just is there maybe?
We haven't tried that. I mean, the problem with quantum annealing is really that it's not able to cross these perturbative crossings. So yes, we could change the annealing time, for example, or the schedule a bit, but I don't believe that it's still able to do this then. So yeah, the real effect is really from changing this problem Hamiltonian.
I mean, if it would be beneficial for this.
Yeah, sure. I mean, the total runtime of the algorithm has two parts. That's the number of avoided level crossings that exist in the spectrum with the ground state and their size. This is how quantum annealing scales. What we make with learning-driven annealing is that we remove this dependence on the gap size, because we can just tell the system what to do at small gaps. But of course, we still have the number of gaps that we have to cross. And if quantum annealing itself is more able to cross more of these, so we have to correct less, then of course it performs better. Yeah.
More questions over there. Oh, I don't remember who's first, but let's go with an order.
Hi, thanks for the really nice talk. I have a few simple questions. So, can you think of any cases in which this learning iteration wouldn't actually help you basically like pump out those local minimum, right? And like guide your solution trajectories more towards the global minimum?
Yeah. Honestly, we haven't found any, but it's, I mean, so we know that in quantum annealing, we're very sure that there's just a many-body localization, there's perturbative crossings, and there are transitions within a valley. We have algorithms for all of these three, so in principle we can correct any transition that happens. I mean, I haven't seen a problem yet where I couldn't really use this and couldn't find a solution. As of course doesn't mean anything. Yeah, it's hard to study this, because when you look at small scale problems like 20, 30 qubit problems where you can really simulate what's going on, you have to really manually engineer bottlenecks into the spectrum to make it hard, so that quantum annealing fails. And of course, I can only engineer what I know. So maybe there's some other kind of transition, but yeah, we don't know.
And just one more very, very simple question. I think this is probably because I didn't fully get it. When you do your learning iteration, you make the feature Hamiltonian, you take the suboptimal solution you get in the first iteration, and then find all the terms in the Hamiltonian where for that suboptimal solution, it gives you a negative answer, right? Like it,
yeah.
And then you, presumably in the next iteration, you just make those terms a bit bigger.
Again?
Do you make those terms that were negative in the feature Hamiltonian bigger in the next iteration?
No, we don't. We don't change their strengths. So their strengths are just depending on what's really given in the problem Hamiltonian. So effectively, if there's a coupler and has a certain strength, then we'll also always have the strength. But you force this Z2 symmetry, for example, you force it to one direction. So it's only satisfied, gives us a negative value for one configuration of the two qubits. So we're not adding any strength with every iteration. It's more that you run this, you get new samples, and these samples tend to agree more, so you can modify more couplers, more biases in the end. So it's really the amount of couplers or the amount of feature Hamiltonian that we apply.
Thank you.
Right. Sorry. Yeah, you're next.
Thanks again. I've been asking many questions to you in the last months. But I wonder, since we have time, if you could give a little bit of more physical intuition on the global search protocol. So how does it work? And then just a quick, simpler question to answer. Have you been applying this to real NPR problems? And like up to what size do you think it's going to be competitive against classical heuristics, like say on, I don't know, whatever, traveling salesman problem, scheduling problem, you name it?
Yeah, so maybe the last question first.
Yeah.
It depends on how well your quantum annealing really works. So in the worst case, a quantum annealer is just doing thermal search, and we just match whatever you can do with simulate and annealing, basically. Simulate annealing would also benefit from this, because you're simplifying the energy landscape. But in principle, there's no limit in that sense. It's just that we have to deal here with the 5,000 qubits that we have on the DWave. We cannot run any larger problems. Regarding the physical intuition here, Yeah, it depends on how much you want to really see this. Maybe we can talk about this afterwards. But the real idea is really that we can, that we want to isolate these single transitions here. And once you only have this transition here, you know that the system will, since this is a relatively wide gap, these many-body localizations, it will end up in both wells. You will sample states from both wells. Then you can really say, okay, I know I have these samples that belong to my initial well. Okay, the other well, I want to go to the other states that are far away. So really get these samples where you have states that have a small Hamming distance and some that have like 200, 500 Hamming distance. Yeah. So it's really about, so this instantaneous spectrum, you can really think has a hierarchy in it. And basically what happens is you follow this instantaneous and at some point you will leave. This is what you want to correct. You want to continue walking along this blue curve in this case. Yeah.
A quick question. I think in one of your factorization graphs that you showed, it was becoming worse at one iteration. Like the small qubit, the top one, like the smallest number of qubits.
Yes.
It seems the orange is worse than yellow.
Yes. So in this case, we are interested in finding these bits A and B. And of course, there can go many things wrong within the multiplication circuit, but we can still find these numbers A and B. So in this case, this was still solving the optimization, so we would still find the solution, but it's just that within the multiplication table something went wrong. And this is why then some of the qubits are not correct, and you have this Hamming distance.
Okay.
Any more questions? Yeah.
Hi, so you mentioned this briefly, but if you were to replace the quantum annealing with simulated annealing, how well would this protocol still work?
Yes. So we also tried this. You can find it in the paper if you want to. It does improve. So in this case, we could get from like this 20 hours simulated annealing to I think like an hour, whatever. I mean, it simplifies the NG landscape, so it's clear that it also helps simulate annealing. But the idea really is that in this case we are really focusing and acting on this instantaneous spectrum. So if quantum annealing has less transitions that we need to fix, then it will always win above simulated annealing. But yeah, of course.
Cool, thank you.
Use it classically.
All right, we have time for one more question, maybe. But in that case, actually, I actually might have something. So, like it looks a little bit like with your iterative procedure, you kind of turn the target Hamiltonian over time into like something that looks like the Grover search type of Hamiltonian, right?
I mean, Grover search is really flat and has then one state that goes down. So this is actually the worst case that you could do.
Yeah, that's what I was wondering, actually.
Actually, you turn it into, so in the best case, if you really apply just this feature Hamiltonian completely to a state, you get like this completely monotonic well or landscape. And this is actually mimicking what you have in the driver. So if you like take the driver, the sum of Pauli X, and just rotate them into the Z bases, then you also have this very monotonic well, basically. And in this case, this is actually why it works so well and why you have these very large gaps here. It's because it's then just doing single qubit rotations. There's no two qubit interactions anymore. If you really apply this completely, this feature Hamiltonian to a state.
All right. I think I need to think about this, but I believe you. Thank you very much.
Okay.
Then, let's thank Sebastian one more time.